for the exams. So entire physics revision in just one video. Okay, so people might be scared. You guys are scared for the exams, so this video will help you to relieve your stress a little bit, because you can revise entire physics with a teacher rather than doing yourself alone. Okay, so not wasting any more time, let's start the video. Let me start teaching. So 11th physics basically starts with the chapter physical world, and in physical world what you will be learning, you basically learn about the different things you see in this physical world. What do you see in this physical world? In this physical world we see large objects to small objects. What are the largest object? What are the smallest object? What are the fastest object? What is the slowest object? How do you measure speed? How do you measure the weight of something? And basically, along with all those things, you also learn about the fundamental forces. Right? So there are 4 fundamental forces. That is a gravitational force, electromagnetic force, strong nuclear force, weak nuclear force. These are the 4 forces. And you can see the sequence of these forces in the table here. So which force is strong and which force is the weakest, basically. So gravitational force is basically weakest, because and it has a larger distance. Gravitational force you have seen, right? What is its range and all. So basically it acts over a large range. But this nuclear forces and all, they act in a small nucleus. Basically they help in binding the nucleons. You know that proton and this one, all the protons are positively charged. They are present inside the nucleus. But do you really think that it is possible to pack all the positive charged protons together? Will they want to come together? No, they will not want to come together, because all of them are positively charged. So you need a strong force to bind them, right? And also you have neutrons also, which help in binding them. That's why you have neutrons, neutral particles. But to bind all these inside a nucleus, you need a nuclear force which is present inside the nucleus. Like that, you have electromagnetic force. Electromagnetic force is generally combined in one category, because whenever there is electric field, you will have magnetic field. All that you will study in later chapters. But basically all these only happens. These are the only 4 forces. What does fundamental means? Fundamental means basically only from these 4 forces you have derived all other forces. Okay, now let's go to the second chapter. Only this much you have in the first chapter. Okay, so we guys think that we have so much in physics. Actually physics is the easiest subject, because you have very little to study. We just complicate things. Questions are a little hard, so you need to practice a lot of questions, but theory you don't have much. Okay, so let's not complicate it much. Now the second chapter is units and dimensions. So basically, what is units and dimensions? Units means what? To measure something in the world. If I want to tell my height, with respect to what is my height this much? So for example, if I tell my height is say 5 feet, so you understand. So in ancient times, so feet means basically, okay, like a human's leg, size of human leg, 5-6 legs if you fit, that is the size of 1 feet is this much means. So 6-7 feet, if 8 feet if you join, you will get length. That is what you used to measure length with. So you keep a standard unit. So whenever you want to measure something, so basically you want to measure the weight of somebody. So how will you tell the weight of somebody is how much? You need to measure it with respect to something, right? Otherwise it's very difficult, because there is nothing standard in this world. So these units were made by us, that is human beings. It's not created in the nature by itself. There is nothing called a centimeter, nothing called as kilogram, all that. We took a substance and we set a standard that this is 1 kg, this is 1 gram. And whenever there are 1000 such grams, whenever the weight of an object is equal to 1000 such grams, that time it is considered as 1000 grams. And same way we set up the size as 1 centimeter. We fixed a length, standard unit, 1 centimeter will be this much. So when you have 1000 such 1 centimeters length, it means 1000 centimeter. So that's unit. Unit is nothing but they are 7 again fundamental units which are given by us, and these units keep repeating. We repeat the units multiple times, and then we put a number and give the unit after it. So 7 centimeter means 7 centimeters, 7 into centimeter. Got it? So next, what do you have in this chapter? So next most important thing is dimensional analysis. So basically 7 fundamental units are there. You can look at the 7 fundamental units. You have mass, time. For time you have second, then for mass you have, and there are different systems also. So when they started making this unit, somebody has to take care, right? What is centimeter? Centimeter means this much. Who takes care of that? There has to be somebody, right? Like that. So different systems were there. There was an FPS system, which is foot, pound, second, where foot is unit of measurement, pound is unit of weight, and second is unit of time. And then you have CGS system. CGS system is some people who use CGS system, it means they measure length in centimeter, gram, weight in gram, and mass in gram basically, and time in second. And then you have MKS system, mass kilogram second, like that. Okay, so basically this is what you have in units. And then you have measurements. How do you make measurements? I want to measure something. Now I know what are units basically, but how do I measure? How do I know what is the weight? How do I know what is the length? So basically in our book we have length. So how do you measure length? You have something called as vernier caliper, and you have something called as screw gauge. I will tell you further how to use the screw gauge and how to use the vernier caliper. But for now, let's learn about errors. Because whenever you do some calculation, whenever you make a measurement, there is obvious chance of error, right? We are all human beings and we do lot of errors, right? So what is this error? Error is nothing but the deviation from the actual value. If the actual value is say 10 centimeter, the actual reading is 10 centimeter, an object is 10 centimeter, but my device shows it is 10.1 centimeter. Or when I measure it, I get 10.1 centimeter, or I get 10.5 centimeter. It means that my error is 0.5, my error is 0.1. So error is nothing but mistake. It shows there is some deviation from the actual value, right? And that is represented by delta x. So the error here was 0.1 or 0.2. The actual reading is 10 centimeter, but I get a reading which is say 0. Reading this, so actual length of an object is say 10 centimeter, I get 10.2 centimeter. So 0.2 is the error. And what is absolute error? 0.2 divided by 10. Whatever is the length, I need to divide the error by the length. That is called relative error actually. And then when you multiply the relative error into 100, you get the percentage error. Okay, so relative error into 100 gives you the percentage error. And how do you find absolute error? Absolute error is when you don't have the errors, they have not given you the error of a quantity. How do you find errors? In that situation, you will take many measurements, you will take the average of all the measurements. So you will measure a quantity again and again. For example, I will measure the weight of an object. I will measure the weight of this bottle, for example. I measure the weight of the bottle, for example 2-3 times I measure the weight, then I take the reading and I add all the readings and then take the average. So what is the average weight? Different times I got different readings, for example. So all the different readings, so 10.1, 10.2, 10.3, different readings I got. All that I will take average and I will subtract each value from that average. So I got the average say 10.15. I subtract the 10.15 from 10.1, which was initially what value I got. First reading was 10.1. Then second reading was say 10.2. So 10.15 minus 10.2 is 0.05 again. Like that I get different values and all those I take average again, and then that is called the absolute error. Okay, so that's how you do it. Now what happens to errors when you add quantity, and how do you represent errors? So when I want to represent a quantity, say I want to represent the length. Okay, so I measured a length, I got length as 10 centimeter, but I know that my scale doesn't show me accurate reading. Accurate means exact reading. It will have some error, right? So my scale shows 10 centimeter, but it can be 9.9 or it can be 10.1, right? So it can be 9.9 or 10.1. I know that my scale has an error of 0.1. So it can be below or above it. So how do I measure the reading? How do I represent the reading? If I want to tell somebody the reading, how I tell him as 10 plus or minus 0.1. Because all these small things are very much essential. So you know gold. If you are dealing with gold, if you are making something with gold, that 0.1 gram is very important, right? Or when you are doing NASA, if you want to go to space, all that 0.1 calculations are very important. So you should know what is the accuracy of your device, measuring device, how precise it is basically, how accurate, how exact value it gives you. Okay, so error has to be very less. So what happens to the errors when you add two quantities? So I have two quantities, 10 plus or minus 0.1, 20 plus or minus 0.1 again. So two readings I have. Now how do I add these quantities? It's easy. 10 and 20 I can add directly because they are numbers. What happens to errors? They get added. Okay. If I want to find the difference between the two quantities, 20 minus 10 is 10 again. But what happens to errors? Will I subtract 0.1 minus 0.1? So is my error 0? Basically overall there was a issue there is an error in my quantity, that is 0.1, but when I take the difference between two quantities, does error get reduced? No, error still gets added, because error will always be there. So when you add or subtract quantity, errors also get added. And when you multiply or divide any quantity, what happens? You take the basically the relative error. So delta z by z, error by that one, and whatever power is there, you multiply the mod of that power. So if you have, for example, you can look here, xa into yb, y to the power b, x to the power a into y to the power b. If I have this quantity, so error in z will be delta z by z, which is equal to mod of a. So you need to take the mod of the power. So if the power is minus, also negative, also still you take the mod of the power, and then you find the solution. And absolute error is nothing but, I told you, it's the mean of all the errors, and subtract individual values from that. So you take the average and subtract every value from that, each value, and that will give you absolute error. And mean absolute error is nothing but, and what is maximum permissible error? What is the maximum error that is permissible or allowed? Basically, whatever is the least count of a measuring device, that is the maximum permissible error. Basically, it's common sense. If you have a scale which measures 1 centimeter minimum, its least length it can measure is 1 centimeter. If the error itself is 2 centimeter, for example, a scale has an error of 2 centimeter, then it doesn't make sense, right? Your scale can measure smallest value 1 centimeter, but its error is 2 centimeter. So it doesn't make practically sense. So least error it can have is 1 centimeter only. So 1 centimeter up and down is fine, acceptable. But with least count 1 centimeter, if it has an error of more than 1 centimeter, it's not correct, right? Then you have a screw gauge and a vernier caliper. So least count of a screw gauge is pitch divided by number of divisions on the circular scale. So what is a screw gauge? Screw gauge is nothing but, it has a screw. When you rotate the screws, the screw goes on top of a linear scale. There will be a linear scale which has lines on top of that, and even the circular scale has lines. Okay, it has multiple lines on it, so readings on it. So when you rotate it one time completely, in one full rotation of the circular scale, how much distance it covers on this linear scale? See, it starts from here, and on one full rotation it covers this much distance. So in that situation, that is called the pitch. How much distance it covered in one full rotation is called the pitch. And what is the least count of a screw gauge? How much is the least value it can measure? That is pitch. How much distance it covered in one full rotation divided by number of divisions on circular scale. How many divisions are there on circular scale? Generally it will be 50, 100. So how many divisions are there on that? That is called least count. So in your questions, they will give that in 2 complete rounds. In 2 rounds of the circular scale, it covers this much distance. So what will you do? You need to find for 1 round how much distance it covers. That is called pitch. Okay, so you need to be careful when you're finding out what is the pitch. Next, vernier caliper. What is vernier caliper? Again, vernier caliper has 2 teeth like structure, and you move something here and the teeth come here. So it has, so here there will be 2 up and down scale. So it will have a main scale and a vernier scale. So main scale will be there and a vernier scale will be there. Or like this I can represent. So this is the main scale, this is the vernier scale. Main scale slides on top of the vernier scale, and when this 2 scales slide on top of each other, that time this vernier caliper closes and opens. Getting me? So number of vernier scales into vernier scale division. So vernier scale has readings. So how many readings it has into each vernier scale division is equal to number of main scale into main scale division. So you need to equate both, and you can find that always there will be equal. Number of vernier scale into vernier scale division is equal to number of main scale into main scale division, because vernier scale is like this, main scale is like this. So how many vernier scale division into what is their reading is equal to how many main scale into what is the main scale reading. So because both will be equal, because this vernier scale is on top of that, overlapping. So this vernier scale is equivalent to how much main scale division, like that. So you find out. And what is the least count of vernier caliper? Least count of the vernier caliper is 1 main scale division minus 1 vernier scale division. And then you can substitute the values, you can do a little bit and you can solve it. Otherwise not required. 1 vernier scale division you can find from the formula above and you can solve it. And reading in both the cases. In screw gauge and vernier caliper, how do you give the final reading? It is MSR plus CSR into LC, and here it is MSR plus BSR into LC. So you take the main scale reading and add the vernier scale or circular scale reading after multiplying it with least count. Okay, so because they are small, right? Those 2 are small scales. Vernier scale and circular scale are small scale. I told you this round on top of that. So you need to multiply it with least count, and then you need to add it to whatever the main scale was giving you the reading. Okay, so how do you find the least count for both the devices? That also I told you. So that's it. This much only is the chapter, and then we go to the next chapter. So next chapter is the and one more thing in this chapter, reading is actual reading minus zero error. So every device has some zero error. Without measuring itself, before I place any object on top of it, it shows some error. That is called the zero error. Zero error can be negative or it can be positive. Negative means if the scale is above that. So basically, when you look at weighing scale also, when you are measuring your weight, you have seen sometimes the scale will be behind. The number will be behind zero. And sometimes the number will be front of zero without you standing on it. If you don't stand on the scale, it shows negative value or positive value. So it can show 1 gram or minus 1 gram without you standing on the scale. So that 1 gram minus 1 gram, if it is behind, it's minus 1 gram. If it is front, it's plus 1 gram. That is called the zero error. So when you measure your weight, what will you do? If the scale was behind, what you need to do? You need to add that 1 gram. And if the scale was front, you need to subtract it, right? Because it is showing you 1 gram extra. So you need to subtract it. If it is 1 gram behind, you need to add 1 gram. So that's what you will do, right? So the formula is observed reading minus zero error. So if the zero error is negative, it becomes plus, because minus negative zero error. Minus and minus becomes plus, right? So you add it. And if the zero error is positive, I told you, you will subtract it. So observed reading minus zero error. That's it. So this chapter is done. Motion. Right, so next chapter is motion. In motion chapter, what do you study? In motion chapter, you don't have much formulas basically. Motion chapter talks about movement of particles. So what is movement? Movement is nothing but change of position of an object with respect to time. See, my hand is changing its position. So every second, its position is getting changed from here. So that is called movement. If its position is the same place, you will not call it movement. With respect to my hand, with respect to my right hand, my left hand is at the same position, then it will not be called as motion. But with respect to that, if it's changing its position in some time, that's called motion. And motion is nothing but displacement by, so velocity. Basically in motion, what all you need to study? Displacement, distance, velocity, speed, acceleration. So displacement and distance is nothing but, displacement is the shortest distance and distance is the actual distance. And then velocity is nothing but displacement by time, and speed is nothing but distance by time, and acceleration is velocity by time. So what are all these things? So displacement by time, so displacement is a vector quantity, it shows the direction. Distance is just distance, its number. And same way velocity is a vector quantity, it shows the velocity in which direction. But speed doesn't show you direction. So when you are seeing the speed in bike, it shows you the speed, it just shows you a number. It doesn't along with the number, it doesn't tell which direction you're going, right? So because that's speed. And then you have acceleration. Acceleration is how fast the velocity is changing, so it's velocity by time. And if you differentiate all these, so you can see the formula. Velocity is differentiation of displacement by time, acceleration is differentiate velocity with respect to time, and wherever you differentiate, you take slope. So if they give you a graph of displacement and time, you take slope of that, you get velocity. If they give graph of velocity and time, you take slope of that, you get acceleration. If they give you acceleration and time graph, if you take area of that, you get velocity. If they give velocity and time graph, if you take area of that, you get displacement. So basically in terms of integration, where integration comes, you need to take area of those two things. What two things are integrating? If you take the area of that, you get this one. And then you have in this chapter kinematic equations. So that is only the chapter. That's it. It's a very small chapter. So kinematic equations means S is equal to ut plus half at square, v is equal to ut plus u plus at, and v square is equal to u square plus 2as. So these are the main three kinematic equations. So S is displacement, U is initial velocity, V is final velocity. Initially, what is the velocity? Then the object is going to start, and V is the final velocity. And then you have motion under gravity. Motion under gravity, because gravity is also constant, acceleration. So all these kinematic equations work only when acceleration is constant. The acceleration has to be constant. Acceleration should not be changing. So velocity is changing, but at uniform rate. That is called acceleration, right? So at uniform rate means acceleration is uniform. So when acceleration is uniform, only then all these three equations work. And same way, under gravity, in gravity, can all these three equations work? Yes, in gravity, you can use these three equations. In free fall, if I take this paper and if I throw it down, can I use these three equations to find its position, its time, how fast it travels, all that? Yes, I can use it. Because gravity is constant acceleration. Value of g, you know, it's 10. So from these formulas only, basically we have derived the two formulas. H max, what is the maximum height object will go. So if I throw something, how much height the object will go, maximum height. So the object goes from here to here and it comes back down. So what is that height, maximum height? That formula is u square by 2g. And then what is the time for the entire motion? So the object goes like this and comes down. What is the time for that? That is 2h by g, root of 2h by g. So that is it, kinematic. And then you have motion in a plane. So motion in a straight line is then motion in a plane you have now. So same formulas, exactly whatever you learned, but here you will deal with vector quantities which will be in 3 directions. In initial chapter you learned only 1 direction, so basically you will represent everything in 3 different directions, and then you will write. So 3 components: x component, y component, z component. So x, that is I cap, j cap, k cap. So you can see, so all the formulas are same, basically everything is same, just you need to do it differently for different directions. And then you have projectile motion in motion in a plane. So when I throw an object like this, if I throw something from here, the object travels like this, right? So every object has 2 components. A projectile motion, if I throw an object, it will have 2 components. One is the x component, one is the y component. X component will be how much? So if this is the velocities in this direction, I'm throwing an object in this direction, so this component, you know, it will be how much? It will be cos theta, right? V cos theta, and this will be V sin theta. So I can split this motion into 2 directions. Now, who's responsible for height? So if I throw a projectile at you like this, or if I throw something this side like this, so from one hand to another hand, so basically if I have this cover, if I throw this cover from this hand to this hand, for it to come from this hand to this hand, who is responsible for the height? How high the cover will go? What is responsible for its height? Basically, obviously the up component, right? The top component of velocity. Velocity has this component, and so this side component and this side component. Who is responsible for its maximum height? This component. Who is responsible for its maximum range? What is the meaning of range? How far it goes. So who is responsible for range? Basically for range, this component, that is cos theta, is responsible. And for height, who is responsible? Basically, so sin theta is responsible. So using those formulas, I can find h max and range. So basically you can see the formula I have given it. It's nothing but u square by 2g and u square by g, all that formula only, whatever you studied only. So basically sin square theta comes and sin 2 theta comes, all that how it comes. You can go further into derivation. It's nothing but range, you know it's which component, and then multiply it by time. So you know the time value, all that, and you will get the derivation. So that is it in motion in a plane. Then you have Rainman and Riverman. How do you do Rainman questions? In Rainman you will get questions. Again, everything is just about vectors. It's nothing to learn. If you are good at math, if you are good at vectors, you can do all the questions. In Rainman, what happens? Rain falls at an angle. At what angle should he hold the umbrella when he is walking at a certain speed? So you need to calculate the relative velocity. Relative velocity is what? It's velocity of A minus velocity of B. So relative velocity of A with respect to B. So whenever you talk about relative velocity, so this hand is also moving. So both my hands are moving with respect to me, for example. Both are moving. But this is moving fast, this is moving slow. Both are moving towards the left. This moves fast and this moves slow. So this will cross it front. Right? So what is the relative velocity with respect to me? What is the relative velocity of this with respect to me? So in that situation, what you need to do is you need to subtract. In that situation, so if you want to find relative velocity of A with respect to B, you need to find the velocity of A with respect to ground and velocity of B with respect to ground and subtract both of them, and then you will get the equation. So relative velocity concept is very easy. Just subtract both. A with B will be A minus B, B with A will be B minus A. And if both are in different direction, it will get added because one relative velocity becomes negative. Okay, so if both are in opposite direction, you will add them. Why? Because one is minus V and another is minus. And you have relative velocity of AB will be, you can write it anything like velocity of AC plus velocity of CD plus velocity of DB, all that if you add. So it should start with A and it should end with B. Then you will have velocity AB. And flag. So you have flag questions. Flag always flutters in the direction opposite to wind. You know, if the wind is this side, it always flutters in the direction of wind, sorry. So whichever direction the wind is in, flag also will be in that direction. And that is man with respect to wind. It flutters opposite to that of man's velocity. So if I am walking front, the flag flutters which side? Back. So it's opposite to the direction of man, right? So it flutters. So if the wind is stationary, there is no proper wind. Wind is standing still. Air is stationary. But if I move front, the flag goes back. So flag flutters in the direction opposite to that of man's velocity with respect to wind. And if man is at rest, wind is at north, then the flag will be at north. And if man is towards east, wind is at rest, then the flag will flutter towards the west. Then you have laws of motion. So basically next chapter is laws of motion. In laws of motion, what you will be learning, again that's a very easy chapter. In laws of motion you will be studying only about 3 Newton's laws. First Newton law talks about inertia. So what is inertia? An object wants to stay at whatever state it is. It doesn't want to change itself. So if an object is moving, it will try to keep on moving, and if an object is at rest, it will stay at rest forever until and unless an external force is applied to it. So that's the exception. So got it? So an object will stay at rest or it will keep moving until you put an external force. So if you go to space, forget about Earth, because in Earth there is friction, that's why objects don't keep moving, they stop after a point of time. But if you go in space, if you push something, it will keep moving. It will keep on going until something comes in front of it to stop it, until there is a force from opposite direction to stop it. Like how our moon keeps on revolving around the Earth, right? So until somebody is trying to stop the moon, until somebody goes in front of the moon and puts a lot of force to that and tries to stop it like a superhero movie, that time the moon will stop. Otherwise it will keep revolving because there is no force to stop it. Just like that, an object stays in motion or it stays at rest. So if this paper is there, this paper will stay at rest until I put a force on it. See, it's at rest. When I put a force on it, it starts to move. That is called law of inertia. And what does inertia depend on? Mass. If an object is heavy, I need to put more force. If object is lightweight, I need to put less force. So it has more inertia. More inertia means more difficult to move. Which object will be more difficult to move? Which is having more mass. Which object will be less difficult to move? Which is having less mass. So difficulty to move an object or difficulty to change the state of an object is called inertia. So an object will have more inertia if its mass is more. So it's very difficult to move a heavy fridge, but it's very easy to move a small toy car because the mass of the toy car is less. So you can change its state easily. It has less inertia. And then you have change in momentum per unit time is force. That is second law. So when momentum of an object changes, that is only force. So an object is traveling towards you. What is momentum? Mass into velocity. If an object is traveling towards you very fast with high velocity, okay, when will the force be more? When the high velocity changes very fast. See, it stops very fast immediately. That means the force is more, right? So a heavy object with high speed changes its speed very fast. That is more force. But if it changes very slowly, the force is less, right? That's why you have seen per unit time. That's why you have seen cricketers and all, when they catch a ball, they catch it slowly. They hold the ball and move their hand behind, so that the time of catching the ball reduces, and that reduces the force. Okay, because if the time increases, force reduces. Momentum is nothing but mv divided by t. Is nothing but force, right? So here you have differentiate both, change in momentum, mv, both differentiate, and then you with respect to time. So when you differentiate mass with respect to time, basically here mass doesn't change. Normally mass doesn't change, so that equation goes off from the formula. Only velocity changes with respect to time. Velocity, when it is changing with respect to time, that is called acceleration. So you get the formula ma. Force is mass into acceleration. Then third law of Newton is nothing but every action has an equal and opposite reaction. So basically, if I press my hand, this hand is also pressing me with same force. So if I put force here, same force is being applied by this hand to this hand in opposite direction. I'm pressing it here, I can feel the press even here, right, in opposite direction. That is called Newton's third law. That's how we walk, in cycle, any kind of motion. Newton's third law only acts. When you push the floor back, when I'm walking, I'm pushing the floor back, because of which floor is pushing me front. See, you can see I'm pushing it back, but something feels like it's pushing me front. So that is called Newton's third law. Okay. And then you have spring force. Spring force is directly proportional to how much ever you elongate it, how much ever you compress it, right? So if I pull a spring more, it becomes more difficult, and if I pull it little, it is little easy. So spring, if I extend the spring more, it put more force on me. If I extend it little, it puts less force on me. So spring force is directly proportional to the pull, the distance, and along with that, it is proportional to what the spring is made up of. It depends on that also. That is only nothing but constant K. So what it is made up of. So force is equal to K into X. And next you have friction. You have static friction and kinetic friction. Static friction is nothing but mu n. Both static and kinetic friction is nothing but mu n. Static friction acts on stationary objects. Kinetic friction, when an object is moving, it exerts mu n force to stop it. Okay, in opposite direction to motion, because of all these friction only. And you have angle of repose, that is tan theta r. So tan theta. So at any angle, what is the friction? That is only theta. So at one angle, if an object is placed, angle of repose means what is the maximum angle at which it can stay at one place only. See, I have an object, I have this cover here. The cover is stationary now. It's not going down, it's not going down, it's not going down. Now it starts to go down. What is this angle? What is the maximum angle? Now it can stay here at rest. Almost at this angle, it can stay at rest. Almost. So this is called theta, and that will be called the static friction, coefficient of static friction, that is mu s. Okay, mu. And then you should know free body diagrams. Force on the objects, force is equal to ma. You add all the masses, you equate all that. So you draw block diagram, you represent every body in this world in the form of block. If there's a car, you draw it in the form of a square. If there's a bike, you draw it in the form of square. If there is human, you draw it in the form of a square. Whatever it is, you draw it in the form of a square, and then you put all the forces, you draw forces in the form of arrow, then you solve it, the equation. Okay, then you also have tension acts upward. You can see pulley. For pulley, what is the situation? You can see it for a block. If two forces are acting in opposite direction, F1 minus F minus F1 is ma, F1 minus. So again, one more thing, I'm really sorry for my handwriting, because it's very difficult. I was using the pen tab to write all this, so it's very difficult. I don't have an experience of writing with the pen tab, so I'm sorry for the poor handwriting. Just manage it. And then you have work energy and power in, say, rotational motion. So rotational motion is what kind of motion? So you know, rotational motion means an object is rotating like this. Okay, what is the difference between circular and rotational motion? In circular motion, objects revolves around something. So an object revolves like this on a circular path. And in rotational motion, an object revolves around its own axis. An object rotates, basically it rotates around its own axis. Like Earth rotating around its own axis is rotational motion, and Earth rotating around the sun is called circular motion. So you have different terms in rotational or circular motion in both. So you have a term called omega. Omega is nothing but angular, angular velocity. Okay, and same like that you have alpha, which is angular acceleration, and same like that you have theta. Theta is angular displacement. Okay, so change in theta means change in angular displacement. So all the formulas that you used for kinematics, all the kinematic equations which were applying for constant this one acceleration, you can use them for this, which is delta theta is equal to omega naught t plus half alpha t square. So alpha is angular acceleration, omega naught is initial velocity, and delta theta is change in position, angular position, angular displacement, and omega square is omega naught square plus 2 alpha delta theta, and omega is omega naught plus alpha t. Okay, so like that you can use all the equations, basically whatever you had, and omega will be angular velocity into r cross r. Okay, so r cross v, r cross v gives you angular velocity, and angular acceleration in terms of normal acceleration will be how much? R cross a, that is alpha, angular acceleration, like that. And then you also have angular component of mass. Okay, equivalent of mass. So what is mass in terms of linear motion? In terms of linear motion, mass tells you how difficult it is to move an object, right? If the mass is more, it's more difficult to change an object. That is inertia. Inertia is directly proportional to mass, right? But in case of angular motion, you have something called as moment of inertia. That means, so in terms of rotational motion, if you want to rotate an object, you might have seen different situations. Like for example, I have this bottle, right? Is it easy to rotate the bottle like this, or is it easy to rotate the bottle like this? See, this is difficult. I have to put more energy, or I have to, it has more inertia basically if I want to rotate the bottle like this. You might have seen, right, when they carry gas cylinders and all, how do they carry it? They rotate it like this. They don't rotate it like this. They don't rotate the cylinder like this on the floor, because that makes the process difficult. So moving an object around the axis is easy. So because moment of inertia along the axis is less, whereas the moment of inertia, if the object mass gets distributed away from the axis, it becomes more. So you have moment of inertia formula for a point. Moment of inertia is mr square, that is mass, into the distance of the at which the point is there, r square. So that is the moment of inertia. Moment of inertia is nothing but how you had mass in terms of straight linear motion, like that you have moment of inertia in terms of rotational motion. It tells you how difficult or easy it is to move an object. Okay, same like that you have force in terms of rotational motion. What is force? That is torque. That is nothing but r cross f, radius cross f. Okay, that gives you the direction of that is torque. Okay, same like that you have different things. Okay, so these are the rotational components of whatever you learned linear. So basically everything is same. You don't have anything very different. It's just rotational aspect of this thing. So you can use the similar concepts here. So there's nothing to explain much. So loss of motion is done. Next you have, and you also need to know moment of inertia of different objects. Okay, you have moment of inertia of a disk across its axis. So you might have you can understand, right? If there's a flat disk, if I rotate that disk like this, it is little easy, whereas if I rotate the disk like this, how difficult it is. So they are different in different axes. Moment of inertia is different. So we'll attach the photo. You can look here, it's very easy. There are just few shapes, and basically all other there is a connection between the shapes, you can see. Okay, so like moment of inertia across a ring is nothing but across a point, because that is mr square. Why? Because the point ring is nothing but extension of a point, right? If you extend a point on a circle, it gives a ring. So moment of inertia is same, and moment of inertia of a disk, moment of inertia of a cylinder across its axis will be same, because disk, when you're extending the disk across the axis, is only nothing but a cylinder. And then moment of inertia of a hollow cylinder and the ring is again same. So moment of inertia of a point object, moment of inertia of a ring, moment of inertia of a hollow cylinder without top and bottom base is same. Then you have moment of inertia of a disk, and moment of inertia of a cylinder is again same, and you can just learn it. And moment of inertia of a rod across in the middle of the axis, and moment of inertia of a rod at the end points. Okay, then also what is center of mass? Center of mass is a point at which you can assume the entire mass of an object to be concentrated. So if the whole mass of the object had to be present in one point, if I want to ignore the entire this one object, then where will I assume the mass to be? That is called the center of the mass. So after loss of motion, now you have something called as work, energy and power. What is work? Work is nothing but, in real life, work means any kind of work that you're doing. But in physics, work happens only when you apply a force, and the force causes a displacement. The object moves in the same direction in which you're putting force. So basically, if I push a wall, will you tell that you have done some work? No, right? Because the wall is not moving in the direction in which you are pushing. But if the wall moves in the direction in which you are pushing, if I push the wall, so if I push my hand like this, my hand goes back, right? So there is some work done on my hand. So what is work done? Work done is nothing but force dot S. Force dot displacement, in which direction the object is moving when you put a force, that is called work done. And why dot product? Because if you put a force upward, if I pull an object upward but the object goes front, so if I have tied a rope, if I'm pulling this paper, say, upward like this, but it goes front, see, I'm pulling it upward but the paper is going front. So in that situation, my work done will involve which force? Not the top component of the force. It involves the force which is in the direction of the motion, right? So work done means force applied in the direction in which the object is moving. So I will take cos theta of that force, whatever angle you are putting the force, you will take cos of that, right? So that's the reason why you have work done is equal to F dot S, which is because you know dot product is cos theta, F S cos theta. Next you have something called as work energy theorem. So it can be represented as WET. Work energy theorem tells you that kinetic energy to change in kinetic energy means kinetic energy final minus kinetic energy initial. So initially, what is kinetic energy? An object rolls from here and goes to the bottom, right? So what is the change in kinetic energy? That will be equal to kinetic energy initial. Initially, what's the kinetic energy, and what is the final kinetic energy at the bottom? And for conservative force, Fx is equal to change in potential energy by position, that is dx. We will differentiate them. And law of conservation of energy, you know, energy is always conserved. Energy can neither be created nor be destroyed, right? So wherever in this universe, entire universe, wherever you see there is energy, it has been converted from one form to other. Energy cannot be created. So you see, in this situation, the object had more potential energy because it's at the top. That potential energy converts to kinetic energy when it comes to the bottom. Like that, there will be changes from kinetic energy to potential, and from potential to kinetic, things can happen. So you can write law of conservation of mechanical energy, that is work done. Total work done will be equal to work done external plus work done internal, and that work done external, if it is 0, then work done internal, or you can write minus delta U, change in potential energy, which is equal to change in kinetic energy, just like how you saw now. So change in potential energy will be equal to change in kinetic energy, because that potential energy only becomes the kinetic energy. So you can see change in kinetic energy plus delta U is equal to 0, or kinetic energy plus potential energy is constant. Okay. Next you have spring force. What spring force? Spring force is nothing but the force that the spring exerts. So you know that is directly proportional to how much you are pulling the spring, right? If you pull the spring more, the spring will put more force on you, and if you pull it less, it will pull less. So that is spring force is equal to K. It's directly proportional to X with whatever that is elongation in the spring, and K is nothing but constant. It depends on the material of the spring also, right? If the material of the spring, if the spring is made up of a strong material, it will put more force, and if it's made up of light material, it will put less force on it. And what is energy? Energy is half kx square. In spring, what is energy? Half kx square. What is the force in a spring? It is kx and minus kx, because the spring exerts a force in opposite direction to what you are displacing it. And energy is half kx square in a spring. And what is power? Power is nothing but work done by time. You are doing some amount of work. So if I do, both of us are doing same work, but I do it in 1 second, you are doing it in 5 seconds. Who does more work? It's very easy, right? You can understand it easily. Person who does it with more power, where power will be more. So if a person is doing same amount of work very fast, it means he has more power. And if the same person takes long time to do a work, it means he's having less power, right? So you can understand power is nothing but work done in how much time you are doing it. So work done by time, or change in work done by change in time, that is called power. And then you have if you work done as force into displacement and by time, so it will become force into displacement by time, and displacement by time you know is velocity. So you can write force into velocity also, right? So with what force I'm applying a force and how much velocity an object goes, if I multiply both, that gives me the power, right? So force into velocity. And what is kinetic energy now? Kinetic energy is nothing but half mv square, half of mass into velocity square. So that is it you have in work, energy and power. And also you have something called rotational motion. What is power in case of rotational motion? Power in case of rotation is equal to torque. You are putting some amount of torque, because force is torque, right? Force into velocity. Here it will be force into omega, angular velocity. Force is nothing but torque here. So torque into, if you put a torque on an object, what is torque? Rotational force. If I put a rotational force on an object, it rotates at an angular velocity. If you multiply both rotation for torque into the angular velocity, you get the power in case of rotational motion. And here it is d theta by dt, angular velocity. So you can see this is it, work, energy and power. Then you have collisions and center of mass. So what is center of mass? How do you find the center of mass of an object? I told you center of mass means where the entire mass of an object can be assumed to be concentrated. How do you find that? So if you have a straight line, how do you find where is the center of mass? So what you do basically, you take one point as a reference, and from there, so this is, if this is the origin, or if this is the origin, you take mass. If there are many masses, two masses are present basically. I have two mass basically. What is the center of mass of both the masses? It lies somewhere in the center. You know that. How do you find that? You find mass 1 into the distance from the whichever point you are referring. So mass 1, if this is m1, into 0 because it's present at origin, m2 into say 10 centimeter divided by m1 plus m2. So basically mass into distance plus all the masses, okay, whatever masses are present, point mass, m1 r1 plus m2 r2 plus m3 r3 plus m4 r4, if so many masses are present, and you divide the whole thing by radiuses, all the radius r1 r2 r3, you get the center of mass position. Instead of mass, you can also use area. If there is any flat object, you want to find the point at which the center of mass lies for a flat object, you can do area also. So area 1 into r1 plus area 2 into r2 divided by m1 plus m2. And same way you use even the, if you have any shape and if you remove some mass from that, if you remove some object, where does the center of mass shift? If you want to find that out, you need to subtract. you need to take the removed mass as negative mass basically. So use the same formula, m1 r1 minus m2 r2 divided by m1 minus m2 you can do. Otherwise what you can do, area, if the area of the plate is given. So you have a plate of area, so you know the center of mass in the beginning situation where it will be there for the plate, and you know center of mass for the removed section of the plate. So only for small plate where is the center of mass you do that. When you subtract both the positions and the masses, when you multiply it using the same formula, you get the center of mass of the final product removed, and center of mass is 1 by total mass of the whole object into mixi, mass into position. So basically same formula you are doing. And for continuous mass system, you integrate all the radius dot dm, all the small mass components you will integrate, and the position and multiply it by 1 by m. And then you have center of mass of a removal part, so that I told you already. For a removed part it will be mx minus mx1 by capital M minus small m. And what is coefficient of restitution? Coefficient of restitution is nothing but v2 minus v1 divided by u2 minus u final minus u initial, or u1 minus u2, whatever it is. Okay, so that's called coefficient of restitution. It shows the elasticity or inelasticity of an object. So v2 minus v1, that is final velocity minus initial velocity, is equal to so initial minus final speed basically. So if you do that, you get initial minus final speed of the objects. So two objects are traveling, right? So when two objects are traveling initially at some speed, when they collide their speed changes, final speed. So that is how you see it. Okay, so if you take one object is traveling at some speed, and this object is traveling at some speed. After colliding, this object goes with some speed, this object goes with some speed, or this object comes in opposite direction, this object goes in opposite direction. So all that. So what is elastic and inelastic collision? Let's understand that first. So elastic collision means when two objects collide, basically they so if one object is stationary and one object is traveling very fast, it travels and it transfers the entire kinetic energy to this object. So what kinetic energy this object had, that gets transferred to this object. So you might have seen in pool games and all, when you hit with the white ball stands there and the other ball goes. That is elastic collision. Inelastic collision means when I say if I hit two magnets, what happens? One magnet is moving and it hits this magnet, and both the magnets start moving at the same speed there. So basically the speed gets reduced because this object had some energy that is transferred to this object also. So both will share half of energy and then they will travel. So that is called inelastic collision. So in case of elastic collision, what happens? Entire velocity is transferred to another object. And in case of inelastic collision, what is happening? In case of inelastic collision, basically the energy of both the objects will remain constant, but the speed gets reduced. That is called inelastic. So coefficient of restitution of elastic collision is 1, and coefficient of restitution of inelastic collision is less than 1. Okay, so you don't have perfectly elastic collisions in real life generally, so there will be some loss of energy in form of sound and other things. Okay, then you have gravitation chapter. In gravitation you will be studying electrostatics also. So similar chapters or similar formulas only you will be having in gravitation. So gravitation is nothing but it is a force between two objects. Two objects attract each other because of their mass. Okay, so you have seen Earth attracting Moon or Earth attracting you. That's why we stick onto the Earth. So force of gravitation is nothing but gmm by r square. Both the masses multiply, product of both the masses divided by the distance between them into g. G is constant in that situation. And here you can see gm by r square is nothing but it is called the gravitational field. What is gravitational field? It is gm by r square. So if you make one mass as 1, if you change the mass of one object to 1 kg, in that situation you will get the gravitational field. And what is so you can see in force is nothing but ma, and you can look here, gm by r square is nothing but small g. That's how you get g value. How do you know g is 9.8, right? We have been using g value, gravitation due to acceleration due to gravity, as 9.8. So that value has come from here, gm into r square. G is constant, you know, 6.626 into 10 power minus 11 something. So like that you have g value you will be having. I will just put the value of g, and m into divided by r square. R, you know, the radius of the earth. So that's how you get the g value, small g. And m2 is nothing but mass of another object. So how much force will be exerted on another object? The force exerted on any object will be equal to ma, that you have been studying, or mg, that is the weight of an object. So you can see the formulas. Then you have gravitational flux. What is gravitational flux? It's nothing but E dot dA. So gravitational potential into dA, which is equal to mass enclosed by 1 by 4 pi g. Okay, so there it was epsilon naught, here it is 1 by 4 pi g, and V potential is nothing but minus gm by r. And Kepler's laws, so you also have Kepler's law. First law tells you that objects which are revolving revolve in elliptical orbits. So whenever a substance is revolving, planets are revolving around sun, for example, they do it in elliptical orbits. And second law of Kepler tells you that radius vector, so radius vector, you know, right? So radius vector sweeps equal areas in equal intervals of time. So at any time interval, so if you say one day, for example, in one day how much area it covered here, it swept how much area. Swept means in one day it started from one point and it came to another point in a day. So how much area did its radius cover? So that radius vector sweep some area, that will be equal to, again one day if you see this side also, it will sweep some area, so that will be equal. So always the radius vectors will be equal. So you can see when it is near the sun, it has to travel faster, right? An object will be traveling faster, a planet will be traveling faster when it is near sun, because it has to cover more distance so that it can sweep equal area. When it is far, it will cover less, speed will be less. Then you have fluid mechanics. So fluid mechanics, and you also have third law of Kepler. Third law of Kepler tells you that the time period square is directly proportional to semi-major axis cube of semi-major axis. Time period of a planet is directly proportional to cube of semi-major axis. What is semi-major axis and semi-minor axis? I have drawn here. Semi-major axis means the big one, big half of the big part of this. If you draw a plus sign, the big line is semi-major axis and the smaller portion, top one, is semi-minor axis. Then you have fluid mechanics. So fluid mechanics, next chapter, you will be studying about flow of fluids. So pressure at any point in a fluid, if you see, that will be equal to pressure at A. So at any top portion of the fluid, if you see, plus rho, density of the fluid, into G, acceleration due to gravity, into H. H is nothing but the height. So of that point, another point at which you know the pressure. So for example, at the surface, you know the pressure. Surface pressure is atmospheric pressure. So atmospheric pressure plus rho gh at whatever height you're trying to find. So you know the pressure increases inside a liquid as you go, because the height or the depth increases. So the pressure inside a fluid increases. So you can see why according to this formula. Then you have Archimedes principle. Archimedes principle tells us that, so Archimedes principle tells us the force of buoyancy. In a fluid, there is a force of buoyancy. That's why objects float or sink. If buoyancy, basically if there is any object, it has less density than the fluid, that means the force of buoyancy is more. The force of buoyancy will become more and the fluid and the object will float on the top. But if the density of the object is more, then what happens? The force of buoyancy cannot match with the density of the object, force exerted by gravity on the object. That's why object sinks. Okay, that's force of buoyancy, and you can see the formula here. So force of buoyancy is nothing but weight of the fluid displaced. Okay, that will be equal to volume of the fluid displaced into this one, basically density of the fluid into G, which is also equal to mf minus mg. Mf into G, mass of the fluid into G. Okay, so mass of fluid into weight, G, will give you the weight of the fluid, right? So weight of the fluid is only nothing but the force that the fluid will exert, maximum force. It's like tension. You have seen, not tension, basically normal force. If I keep an object on top of my hand exerts a normal force on it, right? Like that, water also exerts a force. In the entire water, there will be a force acting on it upward, because of the mass of the water. Inside there is some mass inside the water, right? Because of which it exerts a force on it upward. That force is only nothing but force of buoyancy. Then you have equation of continuity, which tells you area 1 into velocity 1 will be equal to area 2 into velocity 2. So if you take the area in any pipe, so if a pipe is reducing or something, so area of first part into velocity 1 it will be equal to area 2 into velocity 2, and volume flow rate is equal to dv by dt. Okay, that's called volume flow rate. Then you have Bernoulli's equation. What does Bernoulli's principle tells you? Bernoulli's principle tells you the pressure plus rho gh plus half rho v square is constant. Okay, it's just like energy, conservation of energy. So pressure plus rho gh plus half density v square. So basically you divided that equation only, conservation of energy, by m. Okay, so basically you have mgh, here you have rho gh by volume. Basically you are dividing by volume entire equation. So if you divide mass by volume, you get rho gh. If you divide mv square, half mv square, that is kinetic energy. If you divide that by m, you get rho v square. So that's how you get this formula, and that will be constant. And velocity of water coming out of any tumbler, if you have any tub and there is a hole, what is the velocity at which water will come out from the hole? That will be equal to 2gh divided by 1 minus area 2, the bigger area, the top area, by area 1, the area of the whole square. Okay, minus 1 minus area 2 by area 1 whole square. If you subtract that, then you get, if you take the root of that whole equation, you will get the velocity, and generally it is root 2 gh. Okay, if the area of the outside part is very big compared to the whole, generally it will be very big, right? Area 2 is very big compared to the area 1. So in that situation you can neglect that and you will get root 2 gh. Then you get heat transfer. Heat transfer is another chapter. Heat transfer talks about the transfer of heat. Heat is nothing but energy, thermal energy in an object. So delta theta, that is change in temperature divided by time, change in heat. Okay, heat energy of a system. Change in heat energy by time gives you constant into area into T2 minus T1 by x. Okay, and next you also have K into area into delta theta by x. So basically same top formula only I have written. That gives you the magnitude of heat current. Okay, so delta theta, change in heat by time, is nothing but heat current only. It can be taken like current, flow of charges. Here it is flow of heat. And you have delta theta by x Ka, which is thermal resistance. So x divided by Ka gives you thermal resistance, okay, which is I, magnitude of heat current. Radiation, what is radiation? All bodies emit radiation. That's what Provost theory tells you. All the bodies, be it any object, it gives out some radiation. So that is Provost theory. Because objects absorb radiation, right? This white shirt, white is white because it is absorbing all the radiations inside it. All the basically it is emitting all the radiation. It's not absorbing anything. That's why colors. That's why it is white. And why this object is red? Because it absorbs all the radiations except red. It reflects only the red color. Other colors it is absorbing within it. And why this is black? Because it absorbs all the colors. So nothing is reaching your eyes. No color is coming and hitting into your eye. That's why it looks blank. So when it is absorbing all the radiation, it has to give all the radiation in some point of time. So at night, when there is no light, it will be giving out radiations. So that is why you tell that all objects emit, all bodies emit some radiation, some or the other form of radiation. And what is Stephen-Boltzmann law? Stephen-Boltzmann law tells that rate of emission of thermal radiation of a black body. So I told you black body emits radiation, right? So rate of emission of thermal emission of a black body is equal to E, and then you have this constant, and into area, surface area of the body, whatever area it is exposed to, into temperature to the power 4, temperature in Kelvin to the power 4. That's what you get. And that this constant, what I told you, that is nothing but Boltzmann constant. So that is nothing but the Boltzmann constant. So this is the formula, and this is it about heat transfer. And you also have Newton's law of cooling. Newton's law of cooling tells that minus change in temperature over time taken, so an object cooling, that is equal to this formula. You can see 4 into Boltzmann constant into a to the power a into t to the power t naught whole cube by ms into t minus t naught. Okay, s is nothing but specific heat capacity and m is nothing but mass. So every object has some capacity, what heat it can hold within it. That is called the specific heat capacity of objects. Then you have thermal expansion and calorimetry. And thermal expansion and calorimetry, you don't have much formulas. Basically objects expand when you put heat on them. You might have seen, right? So that's why in bridges and all they put gaps between the bridges, because when during summers the objects will expand, the bridge will expand, and then because of that the bridge will break. See, if any bridge is trying to expand, it will break, right? Because there's nothing. So that's why they put gaps between the bridge. So during summers the gaps get closed, and during winters when the bridge shrinks there will be a gap. So same like that in railway tracks also, you might have seen between railway tracks also there will be some gap, and that's why the wires on the roads will be sagging. They don't put the wires tightly, because if they put the wires tightly in winters, when the wire length tries to shrink, wires will break. So that is nothing but thermal expansion. I will just attach the formulas you can see for this chapter. Then thermodynamics and kinetic theory, because you have this in chemistry, for this also you can look at the formulas. I will just put the formulas for this also, thermodynamics and kinetic theory. It's an easy chapter. Basically you have PV is equal to nRT in kinetic theory of gases, that is the main formula. And thermodynamics yes So we are going to start today with 12th physics. In 12th, the first chapter that you have is electrostatics. What does electrostatic mean? When you hear the word electrostatic, what do you understand? Electrostatics basically means electric charge at rest. Okay, static means what? Something is not moving, it is stationary. So when electric charges are at rest, when you study about electric charges at rest, that's called electrostatics. So the first thing that in any situation, in most of the chapters you might have seen, is force, right? So in gravitation also you studied the force between two masses. When you have two mass objects, heavy objects, they have some attractive force between them. That was called, you studied the formula for that. Same way, here you have force that is equal to K, Q1 Q2 by R square. And K is nothing but 1 by 4 pi epsilon naught. K can be represented as 1 by 4 pi epsilon naught. And its value is nothing but 9 into 10 power 9 Newton meter square per coulomb square. So coulomb is the unit of charge. So force you know is Newton, and so the force, if you take everything aside, what unit you get, you can see that. So K Q1 Q2 by R square. So you have two charges, one charge is Q1, another charge is Q2. You need to multiply the two charges, that will give you the force, and it's inversely proportional to the square of the distance between them. So if you increase the distance between them, the force decreases, right? If I increase the force between the charges, that is if I increase the distance between the two charges, the force decreases. So that's the formula. Force between 1 and 2, force on 1, charge 1 due to 2 will be Q1 Q2 by R square, and that's the formula. Next you have electric field. So force is nothing but electric field into charge. That is another thing. Okay, so force is equal to QE, and here Q is Q1 and electric field is due to charge Q2. So what is electric field basically? Electric field is nothing but, you can imagine it as an imaginary region between a charge where it will exert a force on any charge particle. So if I take any external charge, this charge, one charge if I have here, this charge will exert a force on another charge, whichever charge comes in its electric field region. So when you take the Q, the second charge, to be 1 unit or 1 coulomb, in that situation you get the force to be the electric field, right? So that will be the electric field because of any kind of charge. So that's the formula. Or electric field can be written as force by test charge, whatever is the test charge, so if you take. So this is how you find the electric field. And you also have something called as field lines, because unlike gravitational force, this is not just attractive force. So gravitational force was just attractive. You have two masses, the two masses attract each other. But but electrostatics is not like that. In electrostatic, positive and negative charges attract each other. Positive charge repels each other. Negative charge repels each other. So if you have two negative charges, they repel each other. If you have two positive charges, they attract each other. And what is charge? First of all, charge is nothing but the charged particles that you study about. So any particle which has excess electron gives you negative charge, and any particle that has missing electrons is positively charged. So like that you decide the charge on an object. So charge on an object will be a multiple of 1.6 into 10 power minus 19 coulomb, right? It will always be in that multiple. Why? Because you know, charge of an electron is minus 1.6 into 10 power minus 19 coulomb, and the charge on any object will be multiple of this electron charge only, because there will be excess electron or missing electron. So that's how you get. And then you studied about electric field. So you studied about force. Force is nothing but QE, or 1 by 4 pi epsilon naught Q1 Q2 by R square. And electric field is nothing but 1 by 4 pi epsilon naught Q by R square. In electric field you have just one charge involved, so you have Q by R square. And you have electric field for different shapes now. So what are the electric field? You have electric field for solid sphere. So if you have a solid sphere means what? The sphere is having mass inside it also. For a solid sphere, electric field is KQR by R cube. KQ into R, at what distance you're seeing it, divided by R cube, that is inside. If you see inside and solid sphere charge at any point, that will be K into Q, whatever is the charge of the sphere, into R, whatever distance you're seeing. Small r represents distance, and capital R represents the radius of the cube, this one, sphere, the radius of the sphere, cube. So you need to cube that. And next is KQ by R square, that is outside the solid sphere. Outside the solid sphere, it's normal, just like a point charge. What you had electric field for a point charge outside, it was KQ by R square. Like that for a solid sphere also you have k cube by r square. Same like that for a hollow sphere also, outside it is k cube by r square. So inside and outside a solid and hollow sphere it is same, k cube by r square. But inside a hollow sphere it is 0 basically. So if you look at the, so I have written it wrong. So inside it is 0 and outside it is k cube by r square here. Okay, so inside a hollow sphere it will be 0 electric field. Next you have electric potential. What is electric potential? Electric potential is nothing but, so you know what is potential? Potential is ability of something to do something, right? So potential is nothing but it's negative of work done. If you see electric potential, that will be negative of work done, or work done minus WAB, which is equal to charge into potential at B minus potential at A. That gives you potential energy. Okay, potential energy, change in potential energy is nothing but negative of work done, and potential into change in potentials, so potential difference into the charge, one single charge gives you the potential energy. Okay, so you get it. What is potential? Potential involves only one charge. Potential energy basically involves two charges. That's why you have another charge multiplied with that. It's nothing but like electric field. Equivalent to electric field is potential, and equivalent to force is nothing but potential energy. Something like that you can think. Then what is potential energy? It's nothing but k q1 q2 into 1 by r final, whatever is the final distance, minus 1 by r initial. So you are changing the distance between two things. So that time potential energy changes. So what is the change in potential energy? That is k q1 q2 by into 1 by r final minus 1 by r initial. And electric field is differentiation of potential. I told you potential is nothing but electric field. Like electric field, it involves only one charge. So if you differentiate potential with respect to the distance, you get negative differentiation of potential with respect to distance gives you electric field, and if you differentiate potential energy, that gives you force. If you differentiate potential energy with respect to x, you get force. I hope it's clear. And then you have Gauss law. Gauss law talks about electric flux. What is electric flux? Electric flux is nothing but electric field into area. So electric field comes out from a charge, right? If this is a charge, there are electric fields coming out of it. So at what area, how many electric fields are passing through an area? So you multiply electric field into the area, you get the electric flux. That is also equivalent to charge enclosed by epsilon naught. So electric flux is nothing but, so if you have a shape, inside it how many charges are enclosed, if you divide that by epsilon naught, you get the value of electric flux. That's what Gauss law tells us about. And then you also have torque. What is torque? So if you have a positive and a negative charge, you have two charges, positive and a negative charge. So when you have two charges together separated by a distance, that is 2 a. So if you have two charges separated by a distance 2a, then you get dipole moment. So there is a dipole. Okay, when positive and negative charges are present together always, it is called as a dipole. So dipole moment will be equal to, that is P. Dipole moment is represented by P. P is equal to nothing but charge, because in a dipole you have same charges. Both the charges are Q. So plus Q and minus Q basically. So Q into 2A, whatever is the distance. If the distance is A, you take it 2A. If it is 2A, you take it 2A. So whatever is the total distance between these two charges, point charges, plus Q and minus Q, whatever is the distance, if you multiply that by Q, you get the dipole moment. And the torque, whenever you place this dipole inside a electric field, so there are electric field in a constant electric field. If you place the torque, what happens? Positive charge will be attracted, negative charge will be repelled. Or electric field, inside an electric field, positive charge will go towards the electric field, negative charge will be attracted. So what happens? It spins. There is a torque on that dipole. So what you do? So the torque will be equal to nothing but P cross E. Dipole moment cross electric field. Cross product means you know sine theta. P E sine theta. And potential energy of the torque will be how much? That will be minus P dot E. Minus P dot E means what? Minus P is cos theta. Okay, dot product means cos theta, you know that. So that's it, electrostatics. It's a very small chapter, so we learned all these things. Next we will be studying about capacitors. So what are capacitors? Capacitors are a device which supplies sudden energy. It stores energy. Okay, capacitor stores energy. It supplies charges suddenly. So you might have seen in camera flashes and all, right? Or when you look at a camera flash, the flash comes instantly. So you need instant current. in any device, wherever you require instant supply of current energy, you use a capacitor. So capacitor is a device which stores charges. It stores positive and negative charges and it supplies them. It's just like a battery, but battery supplies constant current, capacitor supplies immediately, like a static. That's why you have capacitor in fans also, because fan needs initial torque to rotate. Initial that energy, that push is given by capacitor. It gives huge amount of charges initially. So what is capacitance? Capacitance basically it's like a term which tells how good a capacitor is. What's the power of the capacitor? Basically like power. So how strong, how good a capacitor is, that is capacitance. So capacitance is nothing but how many charges it can store per volt, per potential. Okay, in that potential difference, in that energy, how much ever charges it can store, that is called capacitance. So that can be represented as Q by V, right? Capacitance is Q by V. And you have different types of capacitor. You have parallel plate capacitor, in which you have two plates. Both, one plate has positive charge, another plate has negative charge. So here capacitance is nothing but epsilon naught A by D. So epsilon naught A, area of the plate, divided by the distance, because it's inversely proportional to distance, right? Because that is potential. If the distance is directly proportional to the potential here, and area is what, if the area is big, it can store more charges. If the area is small, it can store less charges, right? So that's why epsilon naught A by D. And for spherical capacitor, if you have spherical capacitor, means what, you take two spheres. Inside one sphere there is another sphere. One inside sphere stores positive charges, outside sphere stores negative charges, something like that. So here you have the formula 4 pi epsilon naught R outside into R inside divided by R outside minus R inside. So you multiply both the sphere's radius and divide it by the difference between them. You subtract them and multiply this whole thing by 4 pi epsilon naught. And for an isolated sphere, if you have just one sphere, then you can assume another sphere to be at infinity, another sphere it is to be infinity. So for one sphere it is 4 pi epsilon naught R. That's all. And then you have potential energy. What is the energy stored in a capacitor? Energy stored in a capacitor is nothing but half CV square. Half C, capacitance, into V square. Then that can also be written as Q square by 2C. So if you write C in terms of, so if you write V in terms of C into, so V is what, C is equal to Q by V, you have it, right? So what will be V? V is nothing but, you will get Q by C, right? V is Q by C. So if you substitute Q by C into the formula V square, you get Q square by 2C. And same way you can substitute in terms of V. If you write in terms of V, V is nothing but Q by C. If you substitute Q by C in the formula for V, then if you substitute C value is nothing but Q by V. If you substitute C value, you get half QV. Okay, so these are the three formulas. Basically all the three are same thing. Half CV square, you can remember one and you can interchange them. So half CV square or Q square by half Q square by C, or half QV. Okay, so basically half QV is a formula. You can think of it this way: half QV. If you substitute Q value, which is CV, you get half CV square, and if you substitute V value, that is Q by C, you get Q square by 2C. So that's all. Then combination of capacitors. You can combine the capacitors in different ways. You can keep the capacitors in series, or you can keep it parallel. What is series connection? When one end of capacitors are attached to another end of another capacitor, then it is called series. In parallel, all the capacitors, both the ends are attached together. That is called parallel. So anywhere, wherever you see parallel connection, both the ends of two devices are connected together, that is parallel. And in series, all the devices are attached to one another at the end, that is called series. So in series, 1 by CS, 1 by capacitance, total capacitance will be equal to 1 by C1 plus 1 by C2 plus 1 by C3. And in case of parallel, you just add the capacitance and you get the total capacitance. Then when you put a dielectric between a capacitance, what is dielectric? Dielectric is a device which does not conduct current. It's like a plastic or any material which does not allow the charges to pass. So when you put a dielectric, there is some charge induced in the dielectric, because in the dielectric also there will come positive charges in the dielectric will get separated, negative charges will get separated, right? So what is the induced charge? What charge is induced in the dielectric? That will be equal to QP, that is induced charge, will be equal to what was the initial charge into 1 minus 1 by K. So when you do that, you get the induced charge. And what is the electric field that is induced? That is electric field vacuum. What is the total electric field now? That will be equal to what was the electric field before when it was vacuum divided by K. K is nothing but a dielectric constant. Every dielectric has a value constant that you divided. And electric field outside will be how much? What is outside electric field? That's nothing but sigma charge density divided by epsilon naught. Sigma is nothing but charge density. Okay, so divided it by epsilon naught, you get the electric field in vacuum. Then what is charging? Capacitor has to be charged, right? So capacitor has charges. So the charges has to come and store on that. So what is charging? So when you charge a capacitor, at what rate it will charge? What is the current charge? That will always be equal to electric field into C multiplied by 1 minus e to the power minus t by RC. And discharging case, what happens? R naught basically Q naught, that is. So Q naught into C to the power minus T by RC. So here the constant tau. So tau is a constant at any. So at this time constant, if you see, always 63% capacitor will be charged or discharged. So tau is RC. Okay, R into C. When you multiply that, you get a time constant. At that time constant, always at that time, if you see, 63% capacitor will be charged or discharged. Then you have parallel and Wheatstone bridge network. Wheatstone bridge network, what happens? If you divide this side capacitance by this side capacitance, and if you divide this side capacitance by, so two capacitors are present here, one in the middle. If the ratio of both of these are equal to ratio of both of these, then the middle one can be ignored. You can remove the middle capacitor because no current will pass through the middle capacitor. Then you have that is called balance state. Okay, when this divided by this is equal to this divided by this. Next chapter you have is current electricity. What does current electricity talk about? That is third chapter. In current electricity we will be talking about moving charges. Charges are moving and it's constituting a current. Current is nothing but when charges move. So what is the velocity or drift current? Basically velocity of drift current. So that is equal to E small charge on the electron into electric field divided by m into tau. So here velocity is equal to at, right? You know velocity will be equal to acceleration times acceleration into time. So here E into E by m is nothing but acceleration. So you can see how that came, how you get acceleration. So force is E and then you get time is velocity by displacement, all that things, and then when you substitute it you will get, so velocity, electric field is velocity by L. So all that things when you substitute it, you will find the value of A to be force by m. A acceleration is force by m, right? So force value if you substitute, you will get E by m basically, and then you get, you know, right, force. So basically you studied force is nothing but QE. Divide that by mass, you get acceleration. Multiply that by time, you get velocity, drift velocity. That's all. It's very easy. It's not a big derivation. Then you have current. Current formula will be NEAVD. Current, when you see, that is charge by time. Okay, so number of charges flowing per unit time, that is called current. How many charges are flowing in 1 second basically. If you another formula for current is nothing but I is equal to NEAVD. And what is current density? If you divide the current by area, so wherever you talk about density, what happens? Something divided by volume, mass by volume, like that. So here density is because it's passing through an area, current is passing through some area, that is current density, right? So current divided by area gives you current density, that is nothing but NEVD. From the previous equation we have substituted it, current value, that is NEAVD. If you divide it by area, area gets cancelled, you get NEVD. Then you substitute VD value, that is NEE tau by m. So you get NE square tau by m into electric field. So if you separate that electric field, so this NE square tau by m can be written as conductivity, sigma. Sigma is nothing but conductivity. So I have written it in green pen separately, so you can see, because it's a very important equation. What is conductivity? NE square tau by m. And inverse, reciprocal of conductivity is nothing but resistivity. Resistivity means what? Conductivity means how much current it is allowing to flow. Resistivity means it's opposing the current. So it's nothing but reciprocal of this one. And what is resistance? Resistivity, I told you, resistivity is 1 by conductivity. So that symbol is rho. That tells you the resistivity. But what is resistance? Resistance is nothing but resistivity into length by area. Okay, and resistance at any temperature. So at every temperature, resistance value will be different, because when you increase the temperature, inside the atoms start to vibrate. Because of that, the current will get disturbed. So in some situations, if you see in case of insulators, more electrons will be produced. In case of insulators or semiconductors, if you see, more electrons will start to become free when you heat it, so it starts to conduct current. But in case of conductors, already there are free electrons to carry current. So when you heat it, the electrons create a hindrance. When atoms start to vibrate, electrons cannot flow easily, so resistance increases. So in case of semiconductors and insulators and all, resistance decreases when you heat it, but in case of conductors it's the other way around, resistance increases. So resistance at any time, what is the value for that? Resistance at any temperature, not time, sorry, resistance at any temperature, if you see, that will be equal to resistance at temperature T0 into 1 plus alpha into delta T. Okay, so that's the formula. And then you have Ohm's law. Ohm's law is nothing but V is equal to IR, that is potential is equal to current into resistance. So potential is directly proportional to current, right? So when you remove the proportionality constant, you get resistance, because resistance opposes current. So you get potential is equal to V is equal to IR. Then you have Kirchhoff's law. Kirchhoff's law tells you that you have Kirchhoff's junction law. Junction law, what it tells you? Junction law basically tells you current entering any junction. So if you have a circuit where there are 4-5 wires, if current entering the junction will be equal to current leaving the junction. So how much current is entering the circuit? So if from two wires, if current is entering, from other 2 wires current will be leaving. So what is the total current entering? That will be the total current leaving. So basically that's what. And if one wire is if current is coming through one wire and there are 3 wires attached to that, from at the node, if you see, from the 3 wires, how much current will be leaving totally, how much current was entering. So current entering is equal to current leaving. That's what junction law tells you. And what loop law tells you? Loop law tells you, if you look at any loop, the potentials, it will be 0. If you start from where you start, again if you come back to same point, the potential difference has to be 0, right? Because the difference in potential becomes 0, you are coming back to same point. So that is about Kirchhoff's loop law. Next you have combination of batteries. In combination of batteries, in parallel, the potential will be equal to EMF of the battery basically. So E1 by R1 plus E2 by R2 plus E3 by R3, how much of batteries are there, all those batteries EMF, divide their individual EMF by the internal resistance. Every battery has some internal resistance, okay, and if you divide that by 1 by R1 plus 1 by R2, all the batteries total resistance 1 by R1 plus 1 by R2, that gives you the EMF of parallel. And EMF in case of series is nothing but all the EMFs, if you add, then you get EMF in series. So if the battery is in opposite direction, you subtract the EMF. So if all the batteries are facing in same direction, then you add the EMF. If the one battery is facing in opposite direction, you subtract the EMF. Then resistance also same thing, resistance get added, all the resistance will get added. Then you have something called as a potentiometer. Potentiometer is nothing but it's a device which has a wire. Then you can measure any unknown resistance through potentiometer. You have a galvanometer attached to a potentiometer. When you have a balancing length on wire, you will touch this another wire after connecting resistance. So at some point the galvanometer shows 0 deflection. It is because the current passing through the galvanometer will be 0 at that point. So you can use this formula, potential at AP, at whichever point you want to find potential. So for finding potential, use potentiometer. So you can use potential at AP, so at whichever point you want to find the potential, that will be equal to potential at AB. We know the potential at AB. AB is the wire, and divide that by AB, the length of AB. So potential at AB divided by length of AB, this is called potential gradient basically. So this whole term we will be knowing, that is VAB by AB, length of AB. This term we will know, that's called potential gradient, and multiply that by balancing length. You balanced it, right? AP, that is called balanced length. So at one length it will show 0 deflection, right? So that is called this one. So using this formula you can find it, whatever is the potential. And how do you convert galvanometer to ammeter? Galvanometer is a device which shows deflection. Whenever there is potential or current, it shows deflection. So how do you, it is used to measure, galvanometer it's used to show just whether there is current present or not in any circuit. But you can use this to measure also. So how do you use it to measure? When you attach a small resistance parallel to the galvanometer, you convert it to an ammeter. Ammeter is a device which is used to measure current. Okay, so you can use this galvanometer to measure current by attaching a small resistance to it in parallel. So what happens when you attach a small resistance to it parallel, the overall resistance of the galvanometer decreases, right? So total resistance becomes much more less. So all the current can flow through it. And to convert it to potentiometer, you attach a big resistance to it in series. So when you attach a big resistance to it in series, what happens? It does not draw any current. So because of that, potential doesn't change. There will be potential difference. You can measure potential difference. So basically, if you want to convert it to ammeter, you want all the current to pass through the galvanometer. That's why you attach a small resistance to it in series, so that all the current can flow through the galvanometer. And if you want to convert it to potentiometer, you don't want it to draw any current. It should have infinite resistance basically. That's the reason why you attach large resistance to it in parallel. Then you have B.B. Roy of Great Britain had a very good wife. You can use this trick to remember the color codes of resistors. So these are the sequence in which it is present, so you can remember it. And then you have gold, silver, green. You can I will attach the values of each of this thing in a picture. You can look at it and you can remember the color codes, because resistor is a small device. You cannot write the number on the resistor. It's 10 ohm, 20 ohms, 500 ohms. How much is the resistance? How will you write in such a small device? So you represent it by colors. You put different colors on top of resistor. So you will have a green line, white line, yellow line, like that. You will have different color lines, and the lines in the beginning tells you the numbers. So they will tell you the number, whatever number. Brown means this number, green means something, like that. You have different numbers for it, and using those numbers you can find what ohms, how much ohms is the resistance, what is the resistance of the resistor. So using that you can find, and last numbers tell you into 10 power what, they tell you into 10 power how much ohms it is, like that. So you can look at the resistor color codes. Then the next chapter is magnetism. So basically in magnetism I have attached both moving charges and magnetism and matter. So this is 4th and 5th chapter. So force magnetic force will be how much? Velocity of the charge. So whenever a charge is moving, whenever a charge moves in a magnetic field, it produces force. Because when a charge moves, it produces another magnetic field. So whenever a charge is moving, it has magnetic field around it. So if you place it in external magnetic field, what will happen? Already there is magnetic field, and this charge is creating its own magnetic field. So between those two magnetic fields there will be a force, right? So the force because of a moving charge inside a magnetic field will be Q into V cross B. Whatever is the external magnetic field, V, velocity of the charge, cross B into Q gives you the force. And what will be the direction of the force? Use always right hand rule. So there are so many rules given in a book. They have given this rule, so many, palm rule, all those rules. So you don't have to use multiple rules, just use one rule. Curl your fingers from the direction of velocity. So if the charge is coming towards you and magnetic field is down, so magnetic field is down and the charge is moving towards you, which direction will the force be? V cross B. Just look at the formulas. Wherever there is cross product, you need to curl your fingers from that cross product direction and you will get the direction of force. So thumb gives you the direction of force. Right hand rule, always use right hand, never get confused, always use right hand. From the direction of velocity to the direction of magnetic field is downward, it gives you the direction of force. And force, another formula is for a, this was for a charge, for a single charge. For current it will be I L cross B. So if you have a wire of length L, so wire is coming towards you, I have a wire, so the current is flowing in the wire this side. I need to curl my fingers from the direction of wire current flowing to the direction of magnetic field. Thumb gives you the direction of force. And then you also have torque in this situation will be M cross B. So basically same like electrostatics, whatever you studied, there it was P, here it is M. That was dipole moment, this is magnetic moment. So magnetic moment cross B, that was P cross E, this is M cross B. So formulas are similar, and magnetic moment is nothing but whenever you have a circular wire, in a circular wire whenever current is flowing, that acts like a dipole. There you had dipole, here a circular wire acts as a dipole. So you have N, number of turns, into I, current flowing, times the area, whatever, NIA, that is the formula. And you have net electromagnetic force. So total electromagnetic, the name itself has electromagnetic force. So electric force plus magnetic force, if you add, you get the total electromagnetic force. So electric force is nothing but QE, you learned that, plus V cross B, that is magnetic force. And mu naught value also you can see, mu naught is magnetic permeability, that is nothing but 4 pi into 10 power minus 7 Newton per ampere square. Okay, so that is the formula. And you have Ampere's law. Ampere's law is nothing but just like Gauss law. Here you have Ampere's law, B dot ds. So magnetic fields dot ds gives you mu naught I enclosed, whatever is the current enclosed, because magnetic field comes because of current. Electric field was because of charge, so it was charge enclosed by epsilon naught. Here you have current enclosed into mu naught. Okay, then you have Biot-Savart law. Biot-Savart law tells you that when current is flowing in a wire, what is the magnetic field? Until now you studied about the force, basically, right? Now you are studying about the magnetic field, how much magnetic field is generated. So if you have a wire, if you hold the wire from, and the thumb is pointing in the direction of current, your fingers give you the direction of magnetic field. So at this point, if you see, I'm holding the wire, okay? So this is the wire flowing upward. So basically if you look at it, so if I take this wire, for example this cable, current is flowing upward. If I hold the wire in my hand like this, my fingers give the direction of magnetic field. So how will the magnetic field be? Like this. So if you see the magnetic field at this point if I ask you the magnetic field, it's towards you, right? And at this point magnetic field is towards me, like that. So magnetic field is in round shape. So basically that's what Biot-Savart law tells you. At any point if you want to find the magnetic field for current carrying wire, magnetic field will be equal to mu naught by 4 pi I dl, whatever is the length, small length elements, into r radius, whatever distance you are seeing it. Okay, so at what point you are trying to find out, the distance between that point divided by r cube. So this gives you in terms of vector. When you have a straight line, you find the magnetic field at any straight wire. If you have a straight wire, because of that straight wire, so because of this straight wire, at this point, what will be the magnetic field? That will be equal to theta. So at this point, what it will be? You draw a straight line, you take this angle and this angle. Two angles are there, right? You take two angles. So sin theta 1 plus sin theta 2, if you add that and multiply by mu naught I by 4 pi d, you get the, for a straight wire. Okay. And if you have an infinite length wire, this was wire of one particular length. If there is infinite wire, then theta 1 and theta 2 will become equal to 90 degree, right? So you will get 2. So 2 will become 4. You can cancel this 2 with 4 pi d. So you get mu naught I by 2 pi d. That's all for an infinite wire. That is the formula. Then for a circular wire, you can see for a circular wire, magnetic field is nothing but mu naught I into r square by 2 into r square plus x square multiply whole power 3 by 2. So denominator you take power 3 by 2. So that is the formula for a circular wire. And for circular wire at the center you will get mu naught I by 2 r. So basically x value you can take it to be 0. So that's how you get this formula. So x is what? R is the radius, x is the distance from this circular wire. So if I have circular wire, basically again same thing, same wire. If I take it in terms of circle, what is the radius? That is r, and the distance if I take from this circle, if I take a distance, at what distance? That is x. So x becomes 0 when I'm finding at the middle. So when you take x 0, you get mu naught I by 2r. Then you have bar magnet. For bar magnet you have magnetic field at the top, if you see axial and equatorial position. So you have B into mu naught m by r square r2 cube, basically 4 pi, and another formula also I have written. So at that point, if you see at equatorial, you have magnetic field will be equal to 2 into mu naught by 4 pi into m, magnetic moment, divided by r cube. So that is the formula for bar magnet. Then you have magnetization. Magnetization is nothing but x into h. Okay, so here you have you can see the formula. H is equal to magnetic external magnetic field by mu naught, and so x is nothing but external magnetic field. Because of external magnetic field, the magnetic this one, magnetization. So you get b naught by mu naught, and m will be equal to this thing, and b is equal to mu naught into h plus m, you can see there, and you get h plus m value. You know m is nothing but x into h, right? So you can write m value as x into h. So you get 1 plus x into mu naught h. So that's it. So you know, whenever you place any object inside a magnetic field, especially this ferromagnetic substances or some magnetic substances, they get charged. Inside them magnetic field comes. Okay, so when you place iron nail inside external magnetic field, what happens? Inside the iron nail also magnetic field lines will come. So that magnetic that iron nail also behaves like a magnet, right? You might have seen that. So basically that is what, and you have a graph for that. So when you charge, you get hysteresis curve. That is called hysteresis curve. You can look at the hysteresis curve. So when you increase the external magnetic field, it gets charged, and when you reduce it, it doesn't come in the same line. It retains some amount of magnetic field lines inside it. It retains some magnetic field inside it. So you get like leaf-like diagram. Okay, electromagnetic induction. What is electromagnetic induction? Electromagnetic induction chapter talks about producing electric current because of changing magnetic field. So then, because of magnetic fields, you get magnetic field will be changing, magnetic field lines inside something, magnetic flux. Basically, when it changes, you get electric EMF is induced. So EMF or potential current, basically current is produced. So EMF induced is nothing but d phi by dt minus d phi by dt, because it's produced in opposite direction. So minus d phi by dt, and phi flux in magnetic field you learned, that is b dot ds. Because magnetic field lines through any area are changing, or if the area itself is changing, in that situation you get EMF is induced. So what is current? Current is nothing but minus 1 by r minus 1 by resistance into d phi by dt. Okay, so you know EMF is nothing but EMF by r. you know current is V is equal to IR, or I is equal to EMF by R. So EMF is minus d phi by dt. If you divide that by R, you get current. And you have motional EMF. Motional EMF is nothing but when you move any object. So if I move this wire inside magnetic field is coming towards you, okay? So if I move this inside external magnetic field, current is produced in this wire, or EMF is produced in this wire. Which direction EMF will be produced? You need to curl your fingers from the direction of this wire length. You need to hold the wire in your hand, so it is moving in this direction. I am moving this wire in this direction. So if I hold it like this, I need to curl my fingers from this direction to this direction. My thumb gives the direction of current. So which direction current will flow? In this direction. So you get positive, plus potential will be up and minus charge will come. So plus you can represent here minus. So you can represent this wire as a battery with plus upward and minus downward. And you get EMF is also equal to when you have a spinning. If I have this rod which is spinning inside a magnetic field, again magnetic field is towards you. If it is spinning or if it is spinning upward, you get EMF is equal to B omega L square by 2. Whatever is the length of the rod or length of wire, multiply that by magnetic field, whatever was the value, multiplied by omega. Omega is angular velocity, with what speed it is rotating, divided by 2. So d omega into L square by 2. And you have self-induction. So when you have any kind of wire, inside it self EMF is induced. So when current is changing, so I told you whenever current is trying to increase or decrease, in that situation another EMF is produced in that, such that it will try to opposite. That's what is the direction. Whatever you learned, in which direction current will be produced whenever magnetic field is changing, it will be produced in such a way that it will try to oppose the change. So in self-induction also, inside the same wire also, current changes. So flux inside it will be Li. It will be directly proportional to current if the current is changing, and that constant is called L. That is called self-induction. And for a long solenoid, self-induction is nothing but mu naught by mu naught 4 pi R square L. Okay, that is the formula. And you have mutual induction. Mutual induction is nothing but for in second coil. So when two coils are present, because of one coil, in another coil this EMF is induced. So that is called mutual induction. So flux in second coil is equal to M I1, current in first coil, and flux in first coil is equal to mutual induction into current in second coil. It's directly proportional to second coil current. Flux in first coil. So mutual induction M is the constant in that situation. Then AC generator, EMF induced. So in AC generator you have a coil spins. So two magnets are there which create magnetic field. Between that a coil spins. Because of the spinning of the coil there is current. So what is EMF? What EMF is induced inside the coil? In coil EMF induced will be NBA, number of turns of the coil, B magnetic field you know, and A area of the coil, omega with what speed it is rotating the coil, sin omega t. That is the formula. Okay, next you have electromagnetic induction. That's it, this chapter. Next you have alternating current. So in alternating current, what did you learn? So alternating current is a very easy chapter. Again, you have average of any function. If you want to find the average of anything, it can be current, average of potential, average of anything you want to find out. You take average of that, you integrate that with respect to time, and you integrate only the times, and when you divide both, you get the average of any function. If you want to find the average of current, or average of velocity, average of anything you want to find out, square of that. So average velocity square, average current square, average potential square, any average square you want to find out, you take function square, that whatever thing you are finding average with respect to time, its square, divided by only times, all the times. If you integrate, you get the f square. And if you want to find f RMS, so if you want to find I RMS, current RMS square, or potential RMS square, or any velocity RMS square, like that. So V RMS, IRMS, if you want to find anywhere RMS term, RMS means root mean square. So you need to find the average of that function square. Okay, so squares average you need to find, and you need to take the square root of that term, you will get RMS. Then you have AC current is sinusoidal, because you represent it in sine wave, because it keeps changing its direction continuously. AC current changes its direction continuously. DC current means direct current. It used to flow directly in one direction. Alternating current keeps changing its direction. So here you have time period of an AC current is 2 pi by omega. Omega is nothing but the this one, angular frequency. So 2 pi by omega, and I is equal to Im sin omega t. Current will be equal to maximum current into sin omega t, because it's a sine graph, so sin omega t. AC voltage applied to a resistor is nothing but potential is equal to Vm sin omega t, and current is Im sin omega t. If you attach a AC voltage is represented by sine symbol inside a circle. In DC voltage you used to represent by battery. You know how you represent a battery: straight line and a small line, big line, small line, that you put in a circuit. It was represented here. AC is represented by sine, and Vi is equal to, that is power, right? Power is IV, so power will be equal to Vm Im sin square omega t, and you have maximum current, which is Vm by R. Okay, so you know V is equal to IR. From there only maximum current will be equal to maximum voltage by resistance, whatever resistor you attach. Then you have a capacitor. When you attach it to a capacitor, whenever you attach an AC source to a capacitor, you get V is equal to Vm sin omega t, I is equal to Im sin omega t plus pi by 2. So there is a phase difference of pi by 2. So current and potential, between current and potential, you can see there is a phase difference of pi by 2. And Im is equal to Vm by Xc. Here instead of R you get Xc. That Xc term acts as a this one, resistance. It behaves like a resistance, and that Xc is nothing but 1 by omega c. Okay, and then you have inductor. For inductor you have Vm sin omega t, Im sin omega t minus pi by 2. So here it is lagging by pi by 2. There it was ahead by pi by 2. Phase difference was pi by 2, front current, and here current value is minus pi by 2. So current is lagging by pi by 2. Here also you have Vm by XL. So here XL value is nothing but omega L. Okay, that is resistance, reactance. Basically this is capacitive reactance, this is inductive reactance. Okay, so two terms. It is like resistance, it behaves like resistance, it opposes current, but it's not exactly resistance. So capacitor, in capacitor Xc means reactance, capacitive reactance. So C stands for capacitive, X means reactance, and here XL means inductive reactance. So it's nothing but resistance only, but you represent it by X, so that is the value. And you have LCR circuit, again you have this one. So you have Z, impedance. Okay, impedance is nothing but, again it behaves like resistance only. So impedance value is R square plus Xc minus XL whole square. If you take square root of this whole term, you get impedance, that is represented by Z, Vm by Z. So that gives you the Im, maximum current. So I have shown that to you. What is impedance? And cos phi is power factor. It's known as power factor, that is equal to resistance by impedance. So whenever they ask you power factor, you need to take cos phi, which is equal to R by Z. R is resistance divided by impedance. So whenever there are all the three, LCR circuit. LCR circuit means what? Capacitance, inductor and resistor. All the three are attached in a circuit. Then what is transformer? Transformer is a device in which you have a current. Right, current is flowing. This current induces current in another coil. So you will have two coils. So you increase the potential or you increase the current. So for that you use a transformer. Transformer is nothing but IP by IS. Current in primary coil divided by current in secondary coil will be equal to potential in secondary coil divided by potential in primary coil will be equal to number of turns in secondary coil by number of turns in primary coil. So basically, to remember this equation, you can remember power in input power is equal to output power. So whatever power is getting input, that is equal to output power. So you can use it to regulate voltage transformer or to increase the voltage. So basically for all those things you can use a transformer. So IP into Vp is equal to Is into Vs. So from there you get IP by Is is equal to Vs by Vp. That is the transformer. And then you have geometrical optics. Geometrical optics chapter again. Here you have mirrors, lenses, spherical surface, refraction, Snell's law, prism, total internal reflection. Mirrors is what? Mirrors is 1 by V plus 1 by U is equal to 1 by F. M is equal to minus V by U is equal to F by F minus U, which is equal to velocity of image. So if the mirror, if something is moving, what will be the velocity of image? Velocity of the image formed will be equal to minus V by U whole square into velocity of the object, whatever object is moving. Okay, so that, and then you have R. In case of mirrors, what is the radius of curvature? That is equal to 2 times of focal. 2 times of focal length will be equal to radius of curvature. So radius of curvature, if you divide by 2, half of radius of curvature is focal length, where all the parallel rays tend to meet. If you draw all parallel rays, they will meet, right? That is called focal length at a point. That is called focus. So 1 by V minus 1 by U gives 1 by F. M is equal to magnification, basically. M means magnification. Okay, so don't get confused. M is V by U here. There it was minus V by U, here it's V by U, which is equal to focal length by focal length plus U. U is object distance, V is image distance. Okay, so don't get confused with what is V and U. U is object distance, V is image distance. And velocity of image, here V stands, it's not distance, here V stands for velocity. Velocity of image will be equal to image distance by object distance square into velocity of object, whatever is the velocity of object. Then spherical surface you have, so I am here focal length. Their focal length was how much? Their focal length was radius of curvature by 2, right? Here, to find focal length, you use this formula, lens maker's formula. It is called lens maker's formula. So to find focal length of a lens, you need to use lens maker formula, which is 1 by f is equal to mu of lens, whatever is the refractive index of length, divided by refractive index of surrounding, minus 1 into 1 by radius of curvature of first side into minus radius of curvature of second side. A lens has 2 radius of curvature, right? So both the radius of curvature you need to divide by 1 and subtract. Then mu of r by v minus mu of I refractive. So whatever is the mu of refractive surface, so air, outside surface is air, right? So like that, whatever is the refraction, wherever refraction is taking place, that surface mu divided by v minus mu of I incident, wherever the light is getting falling, that surface divided by u gives mu r, mu refracted minus mu incident by r. That is the refraction of spherical surface. So you have a spherical surface, this is mu incident, this is mu refracted, the ray gets reflected. So this is a refractive. This, I have a glass, light falls on this. After hitting this, it bends, it gets refracted. So then the formula is this one. Okay, mu refracted will be what? Refractive index of this glass, that is refracted. Why? Because light is getting refracted inside this medium. Mu incident is how much? It will be 1, because mu incident is air if it is coming from air, or if it is some other surface, you need to put that. And V and U, you know, image distance and object distance. R is radius of curvature of the lens. Then combination of lens. For finding combination of lens, if you attach many thin, small thin lenses, the total focal length will be equal to 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3, like that you add all. And if you put a mirror at the end, if you put a mirror, you need to multiply by 2 and then you need to add same formula, 2 into 1 by f1 plus 1 by f2 plus 1 by close everything and plus add mirror's focal length, whatever is the focal length of the mirror. Then you have Snell's law. Snell's law is mu I sin I is equal to mu r sin r. That's very easy formula. Then you have prism. For a prism, sin A plus A is nothing but angle of the prism plus minimum deviation by 2 divided by sin A by 2, and minimum and deviation is equal to I plus E minus A, whatever is the deviation. And then total internal reflection. Total internal reflection happens at critical angle. So when light falls at some critical angle, at that angle total internal reflection takes place. So continuously the light beam inside that medium keeps reflecting. So basically that is sine of critical angle, because it happens at a critical angle. That will be equal to mu refracted by mu rarer. Here R stands for rarer. So rarer medium by denser medium. Refractive index of rarer medium by refractive index of denser medium. Then you also have speed of light. What is speed of light? Speed of light is equal to velocity of the light in any medium multiplied by mu of that medium. So that is what is refractive index. What is refractive index? The refractive index is nothing but speed of light into velocity of light has to give you the speed of light, which is 3 into 10 power 8 meter per second. So that is C. C value is speed of light value into what velocity the light becomes slow, right? Because of a medium. So that becomes low because of refractive index. If the refractive index of a substance is less, light speed will change like that. So mu is the, and then how many images are formed? If you place two mirrors, there are so many images, right? You might have gone to barber. When you go to barber, you see so many images in the mirror. You see continuously so many images. So what is that? That is nothing but 360 divided by theta minus 1. That will give you the number of images. So whatever angle the mirrors are in barber's shop, mirrors are at 0 degree angle. So how many images will be formed? So basically 360 by 0 minus 1, like that. So whatever angle they are at mirrors, that angle you need to divide by 360 and subtract by 1. That will give you the number of images. And mu decreases as lambda increases. So when you increase the wavelength of light, mu decreases. So the refractive index of a medium decreases. Then you have wavefront, wave optics, next chapter. What is wavefront? Wavefront is nothing but a surface of constant wave where the wave is constant, face of the wave is same. Face of wave is same, and that is called wavefront. Then you have Huygens principle. Huygens principle tells you that to find the position of the wave at any time, you can just extend. You can take every point of the wavefront to be a source. Okay, every point of constant wave, you can take that as a source, and you can draw wave fronts for that, and you can find the position of the wave at any time. Then you have superposition principle, which is y is equal to y1 plus y2, or a1 sin omega t plus a2 sin omega t plus phi. You can just add it. Intensity is directly, intensity of light or intensity of any wave, that is directly proportional to amplitudes of that wave square. And Young's double slit experiment, so Young was the scientist who conducted double slit experiment. He put two small slits on the paper, and then from that slits he passed monochromatic light, and because of that light, when that light passed through those slits, different bands were produced: bright band, dark band, bright band, dark band. So that was the experiment he conducted. And then you have diffraction experiment also. In diffraction experiment, basically you will have just one slit, and because of that there are bands produced. In center you have maxima, very bright band, and above that you have lighter bands, and below it also have lighter. Between that you have black bands. So basically light interacts with each other. Light wave, maximas, and so light has two different phases. So those two phases react with mix with each other and form bright spots or dark spots. Okay, so that's how this bright bands and dark bands are produced. Then you have polarization of light. So polarization of light, basically what happens in polarization, light, only one phase of the light. So light has different electric and magnetic fields and all, right? So only one field is allowed. So you change the direction of that light. That is called polarization. When it passes through a Polaroid, only one kind of vibration is allowed through it. Okay, so in different directions you have electric field or magnetic field, whatever. So only one direction field is allowed. So that is called polarized. That is what Polaroid does. Okay, so that is it, this chapter. So basically all other chapters are easy. So you have modern physics after this. Modern physics is, again, you have it in chemistry also, similar things you might be learning. So it's very easy chapter. I will just put the pictures of the formulas. You can look at the formulas. You have semiconductors chapter also. Semiconductors chapter is very interesting and it's very easy also. So basically you can look at the formulas and you can read it. So that's it. I have tried my level best to complete the entire physics for you, so that you can watch this video for revising your physics. Thank you very much.